Hello everyone, my name is Kyle Cluver, and today I will be talking about equivalences within linear algebra, specifically dealing with a square matrix, and then we're going to have a series of statements that really all just mean the exact same thing. So let us get to it. So this theorem is actually called the Big Theorem, and it comes from a course I took at a undergraduate study at Augustana College. The Big Theorem is this. It's called the Big Theorem. For a n by n matrix, or a square matrix, the following are equivalent. 1. The determinant of A, our matrix, is non-zero. 2. The columns of A span Rn. 3. The columns of A are linearly independent. 4. Our matrix equation, Ax equals B, has a unique solution for each B in Rn. And finally, our matrix A has a multiplicative inverse. So, all 5 of these statements really mean the exact same thing, and I'm going to prove they mean the exact same thing. But first, we need a little background knowledge. Okay, so you can kind of see here that I have 2 circles. One is going to be a group of all equivalences, and another is going to be a group of all different equivalences. So everything within the 2 circles mean the same thing respectively in this circle. So let's start with the first one. So we have a given matrix A that is R by C, so it's not squared, it's just some number of rows by some number of columns. Then all of these are equivalent. So we have our columns of A are linearly independent. It's the same thing as meaning that there's a leading 1 in each column when A is fully row reduced. So if we take our matrix A, we row reduce echelon form it, get into its reduced fully, there's going to be a leading 1 in each of those columns. It's the same thing as saying that if we take the system of equations with coefficients from our matrix A, you will have at most one solution. Same thing as saying if we have our matrix equation Ax equals B, we will have at most one solution as well. To give you a visual on our matrix A that is R by C, so you can see here that there are 3 rows and 2 columns, so it doesn't have to be squared, but it is row by columns. This matrix here is said to be linearly independent but not span. That is because there is a leading 1 in each column, but there is not a leading 1 in each row. So we can see that linearly independent, there's going to be a leading 1 in each column. That's exactly what we have here. So I just want to give you a little visual on that. So now we have our second group of equivalences, and that would be same thing, another matrix A that is R by C. These are equivalent. The columns of A span is the same thing as saying there's a leading 1 in each of the rows. When we fully row reduce A, so we put in row reduce echelon form of A, there's going to be a leading 1 in each row. It means it spans. It means the columns of A span. Same thing as saying that if we take this coefficients from our system of equations, we will have at least one solution. Could be more, but we're going to have at least one for sure. Same thing as saying that we take our matrix equation Ax equals B, we'll have at least one solution. To give you another visual on what an example matrix would look like that is said to span but not be linearly independent, here we have 2 rows by 3 column matrix where there's a leading 1 in each row. As you can see that the leading 1 is on the top row and then the leading 1 is on the bottom row of the third column, but nonetheless there's a leading 1 in each row, but there is not a leading 1 in each column. So it's not linearly independent, but this matrix is said to span. I just want to give you those little examples on the difference between linearly independent and span based on where the leading ones are. So now we move on to the key component within this theorem of equivalences, is that our matrix A has to be n by n. It's got to be a square matrix. And what a square matrix looks like is that there's the same number of rows as there are columns. So you can see here that we have, how I denoted it is at the first top left you have A11, that means that is the first row, first column. A2, A sub 21 means the position in the second row, but in the first column. It goes all the way down, so you can kind of see that here that there's going to be the exact same number of rows as there are columns. And this is the key point on why the equivalences in this proof actually work. Without this, it would not work. So, what our proof of equivalences actually looks like. So the way that this proof is going to work is that I'm going to assume one thing and deduce another. Once I've deduced that, then I'm going to assume that and then deduce another part. So in this case, I'm going to assume 1, deduce 2, assume 2, deduce 3, 3 to 4, 4 to 5, 5, back all the way to 1. Once I make a full circle, then we have all of everything is equivalent. And the way I chose to do it is 1, 2, 3, 4, 5 in order. If you wanted to, you could do a different order. It does not really matter. I just personally think that going in order 1, 2, 3, 4, 5 makes the most sense to me. So let us get started on this proof. So we go from 1 to 2. We're going to assume that we have our matrix n, or matrix A, excuse me, that is n by n, our square matrix, and that the determinant of A is non-zero. We must show that the columns of A span Rn. So what we're going to do is we're actually going to take our matrix A and we're going to fully row reduce it. We're going to row reduce echelon form it. And in this case, I denoted that our elementary row operations of e sub 1, e sub 2, e sub 3 as just a specified number of elementary row operations. It could take more than 3. It could take 1. It could take 2. I don't know. It could take 14. Not really sure how many it takes, but in this proof, or in the entire proof, I only chose to do 3 just to save time and energy on writing all of them out. So anyways, that we row reduce our matrix A to this new matrix S. And we row reduce S, it's going to be 2 cases, where S either is row reduced to the identity matrix, or S row reduces to a matrix with a row of all zeros denoted Z. So to give you an example of what this looks like, on the top here we have our identity matrix where there's zeros in every single position except for the diagonal going from top left to bottom right. Those all contain 1s. This is identity matrix of any square matrix, but that's what it would look like. On the bottom there, you have a matrix Z with a row of all zeros. You can see that the final row of that matrix has all zeros. It's kind of standard that the bottom row of a matrix with all zeros is the bottom row. So there's your 2 visuals on what our matrix can simplify to. It's going to be identity, or it's going to be a matrix with a row of all zeros. So our proof. So we're going to take our equation that we had, and we're going to take the determinant of both sides. And we can split up the determinant on our elementary row operations because of the elementary matrix lemma. So that's how we can split up that part in step 2. We also know that the determinant of all of our elementary row operations are non-zero. Something that we can kind of just take on faith. If you really want to do it, you could probably do it yourself to prove yourself that they are, but nonetheless they are non-zero. And finally, from our assumption, we assumed originally that the determinant of A was non-zero. Okay, so now this is going to actually imply that the determinant of S that we row reduce our matrix to is non-zero, because you have all of these non-zero values multiplied together. They have to equal a non-zero value. This then means that our matrix S that we row reduce to has to be the identity, because the determinant of the identity matrix is a non-zero value, but the determinant of a matrix with a row of all zeros is 0. So this means that we actually row reduce to the identity. And if you think back of what the identity looks like, it's a row with, or it's a diagonal from top left to bottom right, has a leading 1 each, right? This is the same thing as saying that there's a leading 1 in each of the rows. And thus, going back to our equivalences, that's why they're in the pink there, you can see that the columns of A span Rn. So we have shown what we needed to show. Now going from 2 to 3. We're going to assume that the columns of A span Rn, and then we must show that the columns of A are linearly independent. So what the proof looks like. Since the columns of A span, this implies that there's a leading 1 in each row. And so I gave you a visual on top there of a matrix. There's a leading 1 in each of those rows right there. But since our matrix is square, the key point of why that all these equivalences work, since it's square, this is the same thing as saying that there's actually a leading 1 in each column. And since you get back to those equivalent statements again that I have in the colors there that you can see, going back to yellow, if there's a leading 1 in each column, this means that the columns of A are linearly independent. So I've just shown 2 to 3. Move on to the next one, 3 to 4. We're going to assume that the columns of A are linearly independent, and we must show that our matrix equation AX equals B has a unique solution for each B. So our proof. So we can actually, I just showed you in the first one from 1 to 2 that we can row reduce our matrix A to the identity. I just showed that we actually can do that, and that's the same thing as saying that the columns of A span and are linearly independent, because there's a leading 1 in each row and each column. And that's really just comes back to the whole big key of that our matrix is square. So we start out with our matrix equation AX equals B here, you can see, and then we elementary row operate it until we get to our matrix A down to the identity, just like how I did in the first part. We have to do everything to both sides, and then with a little bit of algebra, you can see that X actually comes out to B triple prime. Since we can get this all the way down to that, that means we have a unique solution for each B in Rn for our matrix equation A equals B. So that was that part. Going on to the next one, we have 4 to 5. So we're going to assume that we have our matrix equation A equals B has a unique solution for each B. We must show that our matrix A indeed has a multiplicative inverse. So since our matrix equation A equals B has a unique solution, this means that it has at most one solution and at least one solution, so therefore it's got to be only one solution, which is the exact same thing as saying, hey, actually our matrix A row reduces to the identity. The row reduces the identity, so that's why you have there, I have the E sub 3, E sub 2, E sub 1, A equals identity, so we can row reduce our matrix A to the identity, and that's what it means. This then implies that all of our elementary row operations multiplied together is actually our multiplicative inverse. Since by the definition of multiplicative inverse, you have to take the inverse times the original matrix, and that will equal the identity. So therefore, we have a multiplicative inverse for A. Since we have A inverse A equals identity, we also have that A inverse equals identity. So you have both cases of the multiplicative identity. So really, you will start with the left side of it. So you have A inverse A equals identity. You can change back the multiplicative inverse into the elementary row operations, and then you can actually move those algebraically to the right side of A until you get that A inverse equals the identity. So there we go. I've shown that we have a multiplicative inverse. And the final part here is that we have to assume that the matrix A has a multiplicative inverse, and then we must show that the determinant of A is non-zero. We actually have two cases in this proof. The first is that we're going to assume A indeed has a multiplicative inverse, and that we need to show the determinant of A is non-zero. So if we take our fact that we do have a multiplicative inverse, we have A inverse A equals identity. Take the determinant of both sides and then split it, kind of skip that step 2 there. So you have the determinant of each individual part. We know that the determinant of the identity matrix is equal to 1. Since we have the determinant of A inverse times the determinant of A equals 1, this implies that the determinant of both the multiplicative inverse and the original matrix A has to be non-zero, because there's no way that we could have one of those being 0 equaling to a non-zero value. So therefore, determinant of A is non-zero. We'll go down case 1. So case 2 is a contradiction. So we're actually going to assume that A does not have a multiplicative inverse, and then we need to show that actually the determinant of A is non-zero. This contradiction of our negated assumption will imply that we actually do have inverse, and that we actually do go back to case 1. So we're going to start with our matrix A. We're going to row reduce it to Z, a matrix with a row of all zeros. We're going to take the determinant of both sides. We're going to split them up. And then we do know that the determinant of all of our elementary row operations are non-zero, just like we did earlier in the proof. We're going to take that on faith, but that is a true statement. We also know that the determinant of a matrix with a row of all zeros is equal to 0. So now the fact that we have all of these non-zero values multiplied by something, so our determinant of A, some value, is equal to a 0 value, this means that the determinant of A has to be 0. Because the only way that you'll get something equal to 0 is if the determinant of A equals 0. It is a contradiction, and that's exactly what it set out to do. So therefore, case 2 actually never really happens, so we only get case 1 ever. So we have just shown that if we have a multiplicative inverse, the determinant of A is non-zero. So I've just proved all 5 of these equivalences in linear algebra to be the exact same thing. And so I'd like to give a thank you out to Stacey Rodman, who was my professor in Algebra College, for this theorem. And a special note that, like I said earlier in the proof, is that this proof can be really completed in any order, as long as you make a full cycle. So in the cases I did 1, 2, 3, 4, 5, back to 1. If you wanted to, you could have skipped around. You could have started at 5 and gone backwards. It does not really matter, but as long as you get back to where it is, then you're good to go. So there you have it. The equivalences in linear algebra dealing with a matrix.